Statistical literacy. It's a new field. It's a big field. Today, I want to interview an expert on statistical literacy. Now, we all know about artificial intelligence. You've probably heard of ChatGPT. Today, I want to interview Chat on statistical literacy. In particular, I'm asking, should we offer a separate statistical literacy course? So the questions will be posed at the top of the slide in red. Chat's answers are in black below. Let's get started. Chat, how would you describe yourself? And this is what Chat said. I noticed at the bottom, Chat said, I don't possess consciousness, which means I don't think the way that humans do. This is important. Chat, what is the ISLP? This is what Chat said. Promoting statistical literacy. Says it was launched in 1997. I understand Chat's wrong there. It was 1994. This is the 30th anniversary. Chat, how does the ISLP define statistical literacy? Chat said it's an ability to understand, interpret, critically evaluate, and communicate. I want to hit on those last three items in this talk. Statistical literacy is essential for decision-making, reasoning, and participation in today's society. Fine. Let's get specific. Chat, how does statistical literacy differ from introductory statistics? Chat said they focus on different aspects of statistical information. Oh, say more. Statistical literacy encompasses a broader set of skills. Okay. Whereas introductory statistics focuses more on concepts, techniques. I like that distinction. Chat views statistical literacy in these terms: understand, interpret, critically evaluate, and communicate. These are broader skills. Let's see how this plays out. Chat, what does introductory statistics study? And it gave the standard list. I focused on statistical inference. Chat, what is statistical inference? Chat gave a standard definition, making predictions about a population based on sample data. At this point, I ask a slightly different question, and I got a very different answer. Chat, what kinds of statistical inference are there? Chat said, broadly speaking, there are two main types of statistical inference. And I thought, I bet I know what Chat's going to say. Chat's going to say confidence intervals and hypothesis tests, estimation, and decision-making. I was wrong. I was wrong. Can you think of the two categories that Chat came up with? Take a moment. Number one, population inference. I don't think I've ever seen that phrase, but I understand it. Yes, we're making inferences about a population based on data from a sample. Yeah, that's true. But as a statistician, I'm saying, well, that's what I mean when I say statistical inference. What's the other kind? Chat said, causal inference. I said, well, yeah, we do that in random assignment, but you're saying based on observational data? That's a different place. So, chat. What kind of statistical inference, because we've got two kinds, what kind of statistical inference is more common in intro statistics? Chat said population inference. I agreed with that. On causal, it said that's an important topic, often introduced later or in an advanced course. And I thought, well, I'm interested in what's going on in the intro course because my students don't take a second statistics course. Chat. What kind of statistical inference is more common in policy debates? Chat came back, causal inference, more common. And it gave some categories. And if you want more information on this, just call up ChatGPT, put in this question. You should get a similar answer. You can follow the detail. Chat. Give me some examples of causal claims involving everyday statistics. I want to know what we're talking about here. Chat came up with almost a dozen. I'm not going to read all of them. I've highlighted the verb in italics, and I want to come back to that after I finish the list. Education, increased access to early childhood education leads to higher literacy rates. Exercise decreases the risk. Raising the minimum wage results in lower unemployment rates. Launching a new advertising campaign boosts sales. Introducing a software update improves. Are you beginning to see a pattern here? Implementation of recycling reduces. Increased police presence leads to. Consuming a diet rich in fruit and veggies lowers. Expanding public transport correlates with. Implementing financial literacy results in. Now, where am I headed? Remember how chat viewed statistical literacy? The very last item was communication. I want to focus on communication. Look at the causal claims. Here are the verbs. Action verbs. The last two are a little bit different. But when I'm teaching population inference, I'm focusing on association and causation. And when I look at words that imply association, I come up with association, associated, correlated, or two-group comparisons. Women live longer than men, typically. Men are more likely to drink beer than women are likely to drink beer, typically. The causation words, cause and effect. The sufficient words, if you do X, then Y will happen. Yes, yes. But you might say, Schield, the examples that chat gave didn't use association or correlation. They didn't use cause or effect or sufficiency. What about those words? They're what I call the between words. A for association, C for causation, B for between. They assert an association, but they suggest causation. What's most common in the everyday media? Action verbs, increases, raises, ups, cuts. Look at the covariation that we often say as statisticians. As X increases, Y decreases. We know that's just a statement of association. Mathematics doesn't talk about causation. There's no operator for causation in math. So when I say as weight increases, height increases, I'm not saying you can expect to grow taller if you eat more pizza. No, that's association. But it suggests causation. Words like linked, leads to, due to, because of. We need to inform our students about these between words as part of the communication part of statistical literacy. There's too much to read here. Look at the first two lines and the last three. These are headlines all on the same subject. First line, 45,000 deaths attributable to uninsurance. 45,000 deaths associated with lack of insurance. Those are straight up claims, but look at the verbs as we move down the list. Tied to, linked to, links, from, due to, because of, die. And then we hit the last three. Insurance kills. Now we're into action verbs. The second from the bottom, lack of health insurance causes. Now they're definitely asserting causation, whereas at the top, we're just saying it was associated. And the last one, lack of insurance to blame. Not only is it a cause, but it's blameworthy, morally irresponsible. What's the point? It's the words that are making the difference here, and our students need to know about those words if they're going to read and understand statistics in the everyday media. Another example of the importance of words, take this statement. Correlation does not imply causation. I'll bet all of us have said it at one time or another. And as people trained in mathematics, we're very clear. When we say imply, that means sufficient. When we say does not imply, that means is not sufficient. But our students are not trained in mathematics. In general usage, to imply something means to support it. So when we say correlation does not imply causation, our students may hear us saying correlation does not support causation. And if so, they're going to say, this teacher makes no sense. As human beings, seeing correlations, connections, associations, that's how we develop our knowledge. Our knowledge of causation. Yes. How can they be saying that? I don't understand. Again, the importance of words, the importance of communication. Now I want to switch to another element of statistical literacy according to Chat, and that's interpreting. Interpreting. So I asked Chat, why doesn't correlation imply causation? Chat said, here's why. It gave a list of reasons. I've only copied the first one. Third, variables may be causing both the independent and dependent variable to change. These are often referred to as confounding variables, confounders. And these extraneous factors make it difficult to determine the true causal relationship between the independent and dependent variable. I thought, well, this is important. Our students should know about confounding. But Chat, nope. Here's where we get what I consider to be not just a big idea, but the big idea in statistical literacy. Confounding. For me, confounding is the element in introductory statistics. And by elephant, I mean it's something huge, but we ignore it. We know it's there, but it's like we just go around it. We ignore it. As teachers, we know about confounding, but it's not in our statistics textbooks. I picked 100 textbooks off my shelves. 80 of them had no reference to confounding in the index or to any synonym. The 20 that had it, it was usually on 1 or 2 pages where we talked about association is not causation, and they used confounding as an example of why it isn't. Ice cream sales and burglaries in Canada. Burglars don't burglar in the winter. You can slip and fall in the ice and hurt yourself. You do it in the summer when it's hot, and that's when people consume ice cream. Yes. So we know about it, but I don't have time when I'm teaching statistical inference, population inference. I'm hard-pressed to get through everything I need to get through. And teaching confounding complicates things. It's not a simple concept. So I asked Chat, should statistical educators teach confounding? I was surprised when Chat said yes. Normally, Chat doesn't answer a question with yes or no. It comes back with well, here are some reasons for saying yes, or here are some reasons for saying no. Here it said straight up, yes, statistical educators should teach confounding. Why? It's a fundamental concept. It's essential for conducting valid analyses, for interpreting findings accurately, and drawing appropriate conclusions. Well, Chat, this confounding, if we do think about it, if we do work with it, what are the words that indicate we've done that we've considered it? Chat said, here are 4 phrases. Taken into account, considered in the analysis, accounted for, controlled for. Our students need to know about these phrases because these are critically important in reading and evaluating statistics in the everyday media. Chat, what techniques control for confounding quantitatively? Chat came back with 3. Stratification. I like stratification. For me, that's what happens in a table when you break out the values of a confounder in different rows. And then you can compare within that row. Does the relationship still hold up? Does it get bigger? Does it get smaller? Does it vanish? Does it reverse? That's the simplest way of taking into account the influence of a confounder without algebra, without computer software, without regression techniques. As far as matching is concerned, usually that's done in acquiring the data, and it's not something I can do after the data is collected. The third one is the big gun for statisticians, multivariable regression. But I can't teach that as a professional. There are specific assumptions that underlie that model. There are diagnostics that need to be reviewed to see that it's applicable. I don't want to teach bad practice. But later on, I'll demonstrate a simple way to handle multivariable regression without software, algebra, or diagnostics. Stay tuned. Part 3, I'm looking again at how Chat views statistical literacy. Should we offer a separate statistical literacy course? And I asked Chat. It didn't say yes, didn't say no, but it said it can be beneficial for several reasons. It gave 5 reasons. I'm reproducing all 5. I'll just mention the headings for each. It focuses on fundamental concepts, allows students to grasp the essence of thinking without being overwhelmed. It emphasizes real-world applications, which can enhance students' critical thinking skills. It's accessible to all. People with diverse academic backgrounds. Not everybody needs or wants an in-depth understanding of statistical literacy. 4th reason, it promotes data literacy. It teaches students how to critically evaluate data sources. And for me, when I think of data sources, I'm thinking of experiments versus observational studies and the different kinds of experiments. Yes, I want my students to know about the data sources. Number 5, why should we teach it? It's a complement to traditional statistics. It gives students a solid foundation, a conceptual understanding, so they can excel in the more advanced statistics courses. So in summary, as I see it, statistical education does need to offer a statistical literacy course based on the quantitative needs of our students. As Ido Gal said, we should analyze news stories, advertisements, posters, press releases, journal articles. How are statistics being used? We should examine the wording used to express statistical ideas. I think statistical literacy should be empirically based. Otherwise, we end up teaching our pet concept. If you like box plots, you're teaching box plots. If I like stem and leaf diagram, I'm teaching stem and leaf diagram. Our students will never see either of those in the everyday media. What do our students see? Studies say, studies show, study reveals disparity, discrimination, inequity. This is where our students are. This is where we need to be. In my opinion, today's students don't know the difference between association and causation. They don't know the difference between disparity and discrimination. They don't know the difference between hard and soft science, between a crude and an adjusted comparison. I'll come back to these later on. In short, they don't know how to evaluate statistics as evidence for a disputable claim. They don't know what it means to take something into account quantitatively. For me, this is a major weakness in today's education. But this is content that statistical educators are familiar with. They can teach it, and we're going to see whether they should teach it. Part 4, I want to investigate a particular statistical literacy course. Yes, it's my course. It uses my textbook. I'm teaching it. That's not the point. I'm hoping that by looking at one example, somebody else will write a better textbook, will design a better course, and teach it themselves at another school. But it gives you some particulars as to what could be done. This is Math 1300 at the University of New Mexico. It meets a math requirement in the New Mexico general education curriculum. It has been taught for the last, this is the third year now, to over 200 students a year. And the textbook, Statistical Literacy, Critical Thinking About Everyday Statistics, was published by Kendall Hunt last year. This textbook, this course has less than a 30% overlap with traditional statistics. How does it relate to traditional statistics? This is how I see it. For me, statistics studies variation. There are two kinds of variation. Random on the right, where we do margin of error, confidence interval, hypothesis testing. As chat says, that's population inference. That's intro statistics. Yes. On the left, we have a different kind of variation, systemic variation. That's what gives rise to comparisons, ratios, and controlling or. This leads to causal inference and statistical literacy. They overlap, but they have a lot of difference. The objectives of this 1300 course, math course at University of New Mexico. Number 1, can identify and evaluate known influences. Can think hypothetically about those that are unknown or unmeasured. Number 2, can evaluate the strength of evidence provided by statistics in the everyday media, in press releases, and in journal articles. Yes. So this is a very different course. It's designed for students in non-quantitative majors. It's a math course. It doesn't use computers or algebra. Yet it talks about context, causation, and confounding. Strong emphasis on using ordinary English. It can be a standalone survey course, or it can be a bridging course for psychology and sociology majors before they take their research methods, Stat 101 population inference. Here are some particulars. How do I see an argument? I view it much like a house where the basement supports the walls support the roof, and the roof holds up the point. And the argument has a point. And the statistics are typically the evidence in the basement. Now, statistics are socially constructed like words. Somebody went out with a question of interest. They decided who to survey, what questions to ask, what data to collect. So the results, the statistics, can easily be influenced. So what's the advice? Take care. All statistics are socially constructed. Now, there are a lot of different influences on a statistic. So I've grouped them into 4 categories, where the first letter of each category corresponds to the 4 letters in care. R and E stand for randomness and error bias. That's traditional statistical inference, population inference. The first 2, confounding and assembly/assumptions. These are what are unique to statistical literacy. As an example, students are going to see the phrase "science says" in the everyday media. They need to distinguish experiments, hard science, from observational studies, soft science. They need to know the difference between ideal experiments, randomized trials, and quasi-experiments. They need to know the difference between longitudinal and cross-sectional studies. But more importantly, they need to know the difference between an experiment and an observational study. As an example, I call this the diabolical denominator. Do you realize that 93% of the people in prison are men? Yet men are less than 50% of the population. Is this a huge disparity? Yes, it's huge. But what else could I compare? Well, I could look at arrests. 73% of those arrested are male. What about crimes reported? Well, you can get that. At this time I wrote this, I didn't have it. But what I really want is crimes committed, because about half of the crimes committed are actually reported. The government in the US does this survey, and they found that crime victims said that 75% of their assailants were men. What's the point? The disparity depends on what you're comparing it with. So if I compare it with the population, the disparity is big. If I compare it with either of the intermediaries, crimes committed or arrests, it doesn't look as big. Doesn't look as big. Same is true for Blacks on the right side. Now, how do my students take something into account quantitatively? They do it using weighted averages. Consider the claim women earn 73 cents for every dollar a man makes. Now, on the far left side, we have men making 64 grand, women making 47 grand. And 47 is about 73% of 64.2. That's where the 73 cents for every dollar a man makes. That's where it comes from. Now, this comparison, it's not false news. It's not fake news. It may be true, but it doesn't take anything else into account. It's a crude comparison. So I take the different kinds of work status, full-time, part-time, and temp and permanent. Group those into 2 categories, full-time, permanent, and everything else. Full-time permanent, the difference is much smaller, 6,600. Among the other, the difference is even bigger. Okay. How does this work out? Look at the right column in the center section. 68% of men work full-time permanent. 58% of women work full-time permanent. You see those numbers in the left column, 64 and 47K? That's a crude association. It doesn't take anything into account. If we wanted to take into account this difference, the simplest way is to give them both the same mixture. In this case, I want to give women the same 68% mixture that men have as a percentage of full-time permanent. When I do that, the female average income jumps up from 46.6 to 53.1. Quite a big improvement. And now I can say, ta-da, after taking into account work status, women earn 83 cents for every dollar a man makes. Controlling for work status removes a third of the disparity, explains 37% of the disparity. So this is how they work weighted averages. Provided the predictor is binary and the confounder is binary, there's no problem. This course has some other things that are very different. The cornfield equations, the necessary conditions for a confounder to nullify or reverse an association. Now, you know about the percentage of the inverse, but the confusion of the inverse. But do you know it in ordinary English? The percentage of men who run versus the percentage of men among runners. At New Mexico, most of my students are ESL, Spanish speaking. They need help on untangling some of these English language nuances. Reading percentages and tables and graphs, very different. And statistical significance can be influenced in observational studies. So what do the students think? 95% say it's valuable in helping them read the news. 65% helpful in developing critical thinking. 32% of the freshmen and sophomores, English, art, and music majors agree or strongly agree it should be required for graduation. These are important feedback measures. I don't get this kind of feedback from teaching my introductory statistics course. Part 5, we should offer a statistical literacy course. Why? It's imperative. Many, if not most, political and social arguments today involve everyday statistics based on observational studies. Confounding is a big issue. So I say students have no expertise on whether an association is due to causation, whether a disparity is due to discrimination. Yeah. Draw a bright red line. But we have lots of expertise on confounding and how an association can be influenced by confounders. Okay. Here's my big assertion. And here's where I disagree with our keynote, our first keynote. For me, statistical literacy is the future. As AI improves and big data gets bigger, HI, human intelligence, will become even more important. You say, really, how is that? HI involves hypothetical thinking about what could, what should have been taken into account. Yes, that's hypothetical thinking. What are my recommendations? Well, I've taught statistical literacy for a long time. Here they are. Number 1, investigate this course. Read some of the papers, maybe buy the textbook. Teach little parts of it. Get your foot wet. Number 2, support offering this course as an option for all of our students. Convert a section of regular Stat 101 to Stat 100, Statistical Literacy. Number 3, teach the course. As teachers, we know the best way to learn a subject is to teach it. Yes, if you have enough time. This is very definite. Here is a list of my recent publications. You can find me on ResearchGate as well. Best wishes. Thank you.